So
Okay. Right. Oh, so now it's recording. Okay, so I'll share my screen. Okay, so thanks for giving me this blog. I guess I'll try to give a quite simplistic overview, and maybe if the time permits, I'll say something about uh, our research and how we're using these tools in what we're doing. Fritzo is here also. He's part of the project, I guess, main person on the project. So if I'm saying something stupid, don't hesitate to let me know. Let's start with the beginnings, and that is the motivation of generalized geometry and how it fits in the in um, in what we know from string theory. So you see wait, can you see my cursor? It's not very visible, but it's like a little translucent dot. Okay, so I want to make a case for saying that normally when we're studying particles, they really feel the say tangent space of some manifold where they move. But with strings, it's slightly more complicated. The geometry they trace is so-called generalized geometry. I'll try to motivate it, and the good starting point, as every time in physics, is with Lagrangian. So if I look at the Lagrangian for string theory, it's this two-dimensional sigma model. There's a I've chosen light cone coordinates x plus x minus, and my string is propagating in some d-dimensional space. This is metric in the target space and B field in the target space. So you do normal things as you would in with particles, namely you find canonical momentum, and you
Ondra?
yes.
Is it only me who have a bad connection, or is it everybody, or is it Ondra? Because I only hear half of a sentence before. Anyway, okay, so it might.
I don't know.
Yeah.
I have a good connection.
Okay,
Yeah.
good.
For me, it's fine what is Ondřej saying.
Okay, good. Anyway, I have another. I just want one comment. So this is my pet. Say that I mean it doesn't really make sense to differentiate with respect to x, functional differentiate with respect to x dot.
X dot.
Because x and x dot are not independent in a functional differentiation.
So what are you referring to?
You write ds dx dot with the functional derivatives.
What should I do instead?
I mean, the simplest would just say the partial derivative of the Lagrangian density with respect to x dot. That would be the simplest solution.
But this is just okay.
But
you mean like S will be actually L instead?
Yeah. Yes.
Oh yeah, sure. Yeah. Oh, sorry. Yeah. Sorry.
You can do that, or you can think of the on-shell action and then vary with respect to x, not x dot. That would also give you the momentum.
Oh, okay. Yeah. Sorry, I really meant L here. Yeah. Right. Yeah. I'm sorry. Thank you. And by I forgot to say that, but that goes without saying. Like yeah, if you have any questions or comments, I probably have many mistakes and stuff. Please let me know. Or it's much nicer to have conversation rather than me saying stuff. But okay, so yeah, so if you do right thing instead, if you put in L and find canonical momentum, you can compose out of P and X sigma Hamiltonian. That's this object. And you see that you can sort of, I mean, now it's sort of artificial, but you can regroup your objects into these two-dimensional. Sorry, so if target space is d-dimensional, target, then this vector is 2D dimensional. So far it seems like a mild change in notation, but I can do that. Also notice that P's, if X's have indices upstairs, P's usually have indices downstairs. So I have object with varying type of indices. It's 2D dimensional, and there's this matrix in between, which we'll later on call generalized Hamiltonian. But anyway, I want to make case for exactly
Ondřej?
because of the yes.
You should probably have small b, right, in the top right corner of the generalized metric.
Small
Just
b. Oh yes,
instead
yeah.
of
Sorry,
capital.
another mistake. Yes.
Okay,
Yeah, the same b as everywhere else. Yeah. I think I started with capital B, and then later on I had capital B for B transformation, so I changed it another order. Yeah, but this is some object which string naturally feels, and you see exactly based on the structure of those indices, I want to make a case for saying that a string actually naturally feels this different type of tangent space. It lives in Tm plus T star m. That's the right place where to study string theory, and there's a dynamical object, the dynamical background on it, which is encompassed in this 2D times 2D dimensional metric, matrix, which is the generalized metric. So this description, this was just for motivation, but yeah. So we see that there's generalized metric naturally arising. It nicely encompasses G and B background fields. It's you might argue that it's not very nice, but what for instance becomes very transparent in this language is T-duality. You know the T-duality. If I just remind you quickly, it's some symmetry observed in string theory, which exchanges momenta and winding modes, and while preserving the spectrum of string. And if you for those who know, for those who don't, you can. It's not important for later. You might know that this also acts on the target space fields, and the transformations are ugly. But if you regroup G and B in generalized metric, it's actually some nice transformation of this matrix. So that's first like a clue that this might be, you might be up to something when reformulating stuff in terms of generalized geometry. Okay, so now that I've hopefully motivated generalized geometry enough, I'll move a little bit to towards as to what it is on more mathematical footing. So as we, you know, as I proclaimed before, for particles and normal gravity, the suitable geometric description is Riemannian geometry. So studying tangent space or manifold and various geometric structures on it. Whereas in string theory, as proposed by, well, as observed in physics, but also proposed in math literature by Hitchin, it's this generalized tangent space. We call it by double TM, and it's the sum of tangent space and cotangent space. So many things extend, and some things are different. What is same is that we had these structures in normal geometry, like commutator and exterior derivative and connection and maybe complex structure. These things can be sort of realized at in generalized geometry as well. But already at the beginning, due to the structure of the generalized tangent space, there's this canonical pairing associated to this geometry. And that's just, you know, if I take some vector and some form from here, so it's a doublet of vectors and forms, I can contract that one form by vector and produce number. This is canonical pairing. And in terms of the structure groups, it already gives you ODD structure group on the nose. So in normal geometry, without any extra geometric data, you have GLN structure, and maybe if you introduce metric, you reduce to SON. But here, you already have the canonical pairing, and that gives you ODD as a structure group. And then if you add this generalized metric, as I showed before, it gives you further restriction to OD cross OD structure group. Okay, are there any questions right now? Maybe I should pause and ask this from time to time, because I really don't see you guys. I when I'm sharing, I only see my screen, so I don't know if you're confused or I'm saying nonsense and you don't like it, or so it would be nice to know. But anyway,
maybe if you could comment more on the. You said that you have some natural objects in the d-dimensional case, where you have some covariant derivative, or you could have some further reductions of the structure group. And how does that correspond to the doubled case? Is there also a natural connection, natural curvature and stuff?
I'll get to that later in a little bit. But yeah, there's a natural bracket, called Dorfman bracket. I'll comment on that later. And connection, you can choose connection. There's some small problems with it. Well, small, maybe a little bigger problems, but many things generalize in generalized geometry. But yeah, I'll get to the bracket in the generalized geometry case in a little bit. Okay. So just to as I mentioned, the structure group is ODD group. What I mean by that is that it's a special orthogonal group of dimension 2D. So it's really if I complexify, it's really this. But by this d comma d, I really mean that it's with respect to split signature metric. So meaning that eta, the metric is of this form. And this is really, split form is really the nicest form, because if you know that when you're studying representations of complex dimensional, complex Lie algebras, many things get screwed up when you go to real forms. But split form is basically like the complex one. So those are really the nicest you can study. Okay, so just to give you a feeling for what these ODD groups are, if you solve the infinitesimal constraint on ODD group, it's saying this, that in block diagonal form, these are blocks of dimension d. There's three independent block components. One is A, which is unrestricted GLD group. GLD subalgebra, and there's beta and B, capital B. These are antisymmetric, both of them. They have different indices. One of them is like a 2-vector with respect to this GLD, and one of them is 2-form with respect to GLD. So you have something antisymmetric up here, antisymmetric down here, and this is unconstrained, and this is the same thing as there. It's just you specify this guy, and you take minus and transpose of it, and you get the lower bottom component, right bottom component. Okay, there's another important thing when you're studying special orthogonal groups. This is mostly why I'm having the seminar after Klaus. Is that you like to study spinor representations of ODD D of any signature, and in here something is you might remember from Klaus's presentation that for defining spinor representation you need polarization. You need to split your vector space to raising and lowering operators, and you define vacuum by killing it by half of your generators. But here this work has been done for you. If you look at this eta metric, and there's natural splitting of phi into t and t star. Those are two components which where if you restrict your eta, so either to t or t star, it's 0. So these isotropic spaces, so-called isotropic subspaces, they give rise to natural polarization. And when you have that, you can call half of generators of this space, raising operators, half of them lowering operators, and you can generate spinors out of vacuum. So how do we do that? Yeah, so isotropic stuff. Right. Yeah. So yeah, I'll get to spinors later. Sorry. But anyway, yeah. So let's remember that there's this isotropic splitting, thanks to looking at the subspaces where eta vanishes. There's the pairing, as I described before. If I have vector and form, I can take this vector and shove it in this form, and this one with this guy, and construct this pairing. This pairing is ODD invariant as it should be. That's how it was constructed. We can also have another splitting of our vector space if we have a generalized metric. I forgot to mention that before, but generalized metric always squares to 1. And when you have a matrix like this, it gives you projection. So you can split V into V plus and V minus with respect to this generalized metric. And it's not the same splitting as T and T star. That's crucial. And it's rather sort of the other extreme, and that is that eta restricted to V plus is positive definite, and eta restricted to V minus is negative definite. So that's what generalized metric gives you. And okay, so now I'll move to forms. So yes, as I mentioned before, we need the polarization for defining spinors. Sorry, I said forms. I'm going to talk about spinors, but forms you'll see in a bit why I did this forms. So you need the polarization that's choosing which of these generators vectors and forms kill the vacuum. So I choose that vectors kill the vacuum, and then we can construct forms by acting with these x's on the vacuum. And when you do this, you have these objects phi, and you can act on them by X, capital X and small x. These are constructed from forms, from wedging forms. So they're really just classical forms with respect to the this half-dimensional space. So X is in T star, so one forms, and capital X. Sorry, it looks the same. These are in T. So I can act with objects from V, which is T plus T star, on these forms, such that in a natural way I can contract them with vectors, and I can wedge them with other forms. So you see that if I do that, this guy lowers the degree of form, and this guy raises the degree of form. So if I look at all the things I get out of this multiplication, it's the whole space of forms. It's all of the forms constructed from T star. Okay. Why I say forms? It's really with respect to the GLD inside ODD. That's this part. So that if I give you this splitting, I'm telling you what the T and T star M is, and then I'm choosing to generate spinors from half of the space, which is identified with forms. Is that clear?
Yeah, I have a question, or at least clarification that I would like to. So, yeah, could you a little bit more connect to why you call these spinors, or how is this relate this more to the spinor case? Is it just the same construction as you did before, but now you have, instead of OD, you have ODD,
right,
and we are using this projections?
So I don't know how far Klaus got, but when so you maybe remember, maybe I'll do it here. I'll go all the way at the bottom, and when we have the Clifford algebra, right? Then we have these objects mu, right? how do we define spinors there? We choose polarization. Usually we would like maybe choose these guys like this, right? And with respect to these, you'll see that it really splits to pairs of objects. Wait, let me call them gamma plus and minus, and they constitute like a pair of fermions, creation annihilation operators. Like this. Oh, mu, right? One. There's no need for one. So, and then I can say I will define vacuum by requiring that gamma minus always gives you 0, and then I generate all the spinors by acting with gamma plus, right? So these are really like, if you want to be physicsy about that, these are creation and annihilation operators, which are fermionic, right? And I have the commutational relations for them. So if I do that, then I'm naturally getting spinors, right? And it turns out that the polarization was a choice here, and doesn't really matter on choice of polarization.
Yeah, so Ondřej, I didn't go into that construction, but yeah, but what was mentioned in my talk was that we always got 2 to the half dimension of
I see.
of spinors.
Yeah, I see. Oh, okay.
Yeah.
Sorry.
But anyway,
then
I think it's
should
good
have
to see.
Yeah.
But maybe the confusion is that people are used to thinking of spinors as the collection of all of these states. That's one spinor. I mean, you're not talking about each state as a spinor by itself. Like a Dirac spinor has many components.
I'm not quite sure if I. The spinor is anything is a linear is linear hull of these objects, like
it's spinor space. Yeah.
Yeah. So I can act with all the pluses on my vacuum, right? Like, and obviously, like every gamma plus has to appear just either none or ones, otherwise it's 0. And then you know if you do the counting for yourself, then you see that there's 2 to the d over 2 dimensional space of spinors.
Right. And if you now act on this with a commutator of 2 gamma matrices, this rotates these states into each other.
Yes. Yeah.
Right? Yeah. So it transforms under Lorentz transformations as a spinor, as the thing that we're used to talking about as a spinor. Just to make this connection clear.
Oh yeah. Sorry. Yeah, I thought this was discussed, but I'll get to that also in a little bit.
And while you were showing these gamma plus and gamma minus, then it maybe is also good to point out that you choose split signature, because then you don't have to have the I in, right?
Yeah. And this is for free in here, because we're in split signature. Yeah, we don't need this. Sorry for scrolling up and down. We don't need this extra I, which really gets you into complexification. It's ugly, and everything has to be taken with a grain of salt. But in split signature, everything's nice. This I is not there, and actually, for me, I've already started with something which is in this polarized form, where I have a creation and annihilation basis on the nose, so I can just say everything's filled by gamma i's. And just to I was gonna get to that later, but not that later, so I can just tell you now. There's a since this V was T and T star, you can choose the basis for each of these. So some vectors and some forms. If you want to be even more geometric about that, it will be derivatives and dx's, right? And then I have it here. Then you can really identify these gamma pluses, the raising operators, with wedging with dxi, and lowering operators with feeding derivative in the form. So it's contraction with del I and wedging with dxi. And you can see that's a nice exercise that if you take a form, some form of given degree, if you act on it with the dx first, dxi, wedge it, contract with partial j, do it the other way around, dx j, you'll exactly recover that canonical pairing for ith and jth element. So you'll get this proportional to I and j. So that's why it actually that's why you can identify this with Clifford algebra on 2D dimensional vector space. Is that clear?
Yeah.
And yeah, you can see, yeah, several more things are apparent from this description, that if you're acting with all the elements of Clifford algebra, meaning wedging with all the dx's and contracting with del i's, you're shifting throughout all the degrees of forms, right? So if you're studying irreducible representations of Clifford algebra, you'll see that the whole space of spinors will be all the forms. However, if as Ricard said before, if you just restrict yourself on quadratic generators here, so something made of 2 dx's or 2 dels or dx and del, then you see that you're preserving even or odd degree of form. So you only, if you wedge something with 2 dx's, you go from, say, 2 forms to 4 forms, right? You never get 3 form. And likewise with contracting with 2 vectors, see. And then you also jump by 2. And if you do dx del, then you're actually preserving degree. So you see that under this quadratic subalgebra of Clifford algebra, which is identified with ODD, your space decomposes, and that's exactly the chirality from spinors, and it will decompose to even forms and odd forms, and these are by themselves preserved. So I said so this forms a irreducible representation of Clifford algebra, and these guys are irreducible spinor representations of the ODD group within Clifford algebra. There's also a natural pairing you can interpret in terms of the forms and vectors. It's called Mukai pairing, and it's super simple. Not that there's any supersymmetry, just a simple thing. That you take K form and you take any form, wedge it with any other form, and take the top degree. So if we're in ODD, yeah, this guy is a sum of any forms of any degree. Likewise, this guy, you wedge them together, and you just read of the stuff which multiplies the volume form, and they will give you a natural pairing on your spinors. Is this more clear now? Do we see why spinors of ODD are actually forms with respect to this half-dimensional space? This guy, T star M, or B is T plus T star. Is it clear?
Yeah, it's better
yeah.
now. Thank you for
Okay.
going through it.
Yeah. Sorry. I thought no worries. So there's a small caveat, and that is that it's actually not true. What I said is not true, and the reason is that if you look at the transformations under this guy, it actually produces an extra overall factor. So those spinors are not really forms of V star, but they're tensored with this not def but determinant. determinant of v to the half power. So this makes actually some trouble later on, and for instance lead to introduction of dilaton in supergravity, but among other reasons. Okay, but clearly you can see that like multiplying two forms is not a valid operation in spinor space of ODD, because you would multiply these guys. That's cool, right? You can multiply forms and produce new form, but you would also multiply these this extra factor, and they would produce for you something of different weight. Whereas here in Mukai pairing, it's fine. If you pair two guys, you actually want them to square to something what's in determinant of V, and there will also be in determinant of V star, and it will be like a nice invariant object. Just multiplying forms is not great with respect to when perceived as spinors of ODD. But okay, and now we'll get to what Standa was asking about. So in normal differential geometry, there's commutator which encodes in it the differentiable structure, and it tells you how to how taking two sections of DM, how to produce a new one. There's a natural this operation is natural with respect to the GL and structure group, meaning that if you change bases, this object is actually invariant. You can calculate in other bases, and it's like you can like pull out those change of coordinates from both of the slots. There's a natural object in generalized geometry, which is well, there's two actually now, because so in normal geometry you knew that there was there was U acting on V, the Lie derivative, and then you learned that this is also commutator, right? But a priori, they were defined in different ways, or at least they could be defined in different ways, and then you see that they actually coincide. But if I wrote it, so actually the statement is that Lie derivative in normal geometry it's antisymmetric with respect to U and V, which is not the case in generalized geometry, and therefore there's two objects to begin with. There's Dorfman derivative, which plays a role of Lie derivative, and there's Courant bracket, which is antisymmetrization of Dorfman derivative. So now there are two different objects, slightly different objects, and there's price to pay. That Dorfman derivative is nice because Dorfman derivative is nice because it obeys Jacobi identity. Satisfy. Whereas Courant bracket, which is just antisymmetrization of this object, it doesn't. So either you work with something that's not antisymmetric but satisfies Jacobi, or you work with something antisymmetric and it doesn't satisfy Jacobi identity. It's your choice at this point. It's also natural with respect to almost the whole ODD, and by almost whole ODD I mean parabolic part, which is this GLD. So this GLD plays the same role as GLN before, and it's also natural under B transformation. So I can B transform my two vectors in generalized geometry, and it will pull out nicely from the Courant and Dorfman bracket, but not with respect to this guy. And that's actually, if you wanted something natural under that, you would have to go to the realm of double field theory. In generalized geometry, it's really just this part which our objects behave nicely with respect to, but not the full ODD group. Okay, so what's the meaning of these objects? So you know from normal geometry what these guys do. If I differentiate something with respect to U, it's really some flow with respect to field U. So it generates some infinitesimal diffeomorphisms of your system. So in string theory, it's really some generalized diffeomorphisms, or in other words, it merges diffeomorphisms with gauge transformations of your theory. And how it does that is, for instance, if I look at the B field and I act with this Dorfman derivative, it has both vector and form. It does it performs normal differentiation with respect to x, but it also adds to it d of one form. So you see, this is really like a gauge transformation, and this is the diffeomorphism, infinitesimal diffeomorphism. So you can say other thing now. You can say that generalized geometry sort of geometrizes this structure of diffeomorphisms and gauge transformations of your theory. Mm-hmm.
Maybe you should say that it's a gauge transformation of a two form. It's
Yeah,
not,
right.
It's not an ordinary gauge transformation of
oh yes, form. Yeah. It just geometrizes the gauge transformation of two form. Yeah, this is one form. And this is two form. There's a way to add these are not the only gauge transformations of supergravity or full supergravity. G and B fits into the big framework of supergravity. It's the NS sector, and there's a way to geometrize the rest, and we'll just touch that a little bit later. But yeah, for now, it's just this. By the way, if you act twice with Dorfman derivative, if you were asking how on earth would I come up with this Dorfman derivative here, you can see that if I do this, acting on, say, B field, and I'll try to rewrite it as one single Dorfman derivative of some object here. Here, I will have reinvented this Courant bracket. So that's a nice way to derive that. I guess that's the original way how people seen it in physics literature. I don't know. I guess for Courant it was different reasoning of some intercalculation. I don't know much about origins on that side of the story. Okay, so there's these things. So when you're studying the generalized geometry over manifold, it actually could be generalized slightly, and in a sense that the structure of Tm plus D star m, that can be really true only locally. And what I mean by that is that over an infinite small patch UI, your generalized tangent space would be of this form TUI, T star UI. But when I'll be passing to other patch, I won't be identifying my vectors. Let's say this is in patch I and this is in patch J. I'll be identifying x plus x with x plus x, but I can twist with two form here. So if I feed in vector in two form, it's one form, so it's to this guy. And therefore I can so-called twist this object and make something more general globally, which is only where this is only true locally. But I still want some things to be behaving nicely, even though I do this twist, and that's nicely encompassed in object called current algebraic. So I'll still have the bracket on this generalized tangent space. I'll have the pairing as before. So even though it's not globally Tm plus D star m, it will be some product. It will be some product on Tm cross Tm. going to real numbers, and there will be so-called anchor map going from Tm plus from capital Tm down to Tm. So I only know how generalized tangent space projects on Tm. I don't really know how Tm sits in general. That was what I wanted to say. Okay. Right. I guess I don't have to get to this. Okay. Is this clear? These objects they will satisfy a bunch of axioms of compatibility, but I don't want to get into that. You can Google current algebra, and I'm just giving sort of overview of objects which are present. Okay, so how is this useful for supergravity? As I said before, it geometrizes and puts on the equal footing diffeomorphisms and gauge transformations of B field. So you can you see that if you specialize the vectors, you have the infinitesimal diffeomorphisms of G and B, but you also have this extra gauge transformation of B. And then if you what's the field content of supergravity? We have these two types, A and B. The NS sector is always the same. It's the metric and B field and dilaton. I won't talk about dilaton, even though I mentioned it before. And there's R sector, which are even forms in A, right? Yeah, even forms in 2A and odd forms in 2B, and you see that that's why I talked about spinors before, because spinors of ODD are exactly the forms of the underlying GLD group. So you see that there must be, I guess there's some connections apparent at this point. We see that these two objects, they nicely repackage in H, the generalized metric, and these objects are playing role of spinors of ODD. So there must be something behind this whole story. It can be coincidence. And right, is it clear? I don't know. Okay. Okay, so yeah, as I said, H nicely repackages the NS sector, and you can do something about OR sector as well. You can put them in spinor representation of ODD. So how do you now? So this is just a brief thing. How do I repackage the equations of motion of supergravity? And this I will just mention very briefly. For instance, Fritz would know much more about this. I have much more to say. So you can define generalized connection, which will be just again connection on generalized tension space, something what differentiate objects here and spits out the objects in the same space with respect to the vectors in generalized vectors in TM. And then it would be natural. Well, I called it something else. Sorry, maybe I should change this to do. It would be natural to construct if we have connection. We all like to construct curvature, because we know in normal gravity theory the equation of motion for G is really that Ricci is 0, right? If there's no presence of sources, so it'd be natural to construct something similar here. So starting with the connection, we can construct this generalized curvature. So I would do the commutator of these, and I would subtract from it d of this current commutator of u and v. So if you this would be a natural curvature in generalized geometry, right? But it turns out that it's not tensorial, and to really have a well-behaved object, what I mean by tensorial, it doesn't transform nicely with respect to the change of coordinates. But it turns out that there's a way out if you restrict yourself on isotropic subspace of the TM, capital TM, not small tm, then you get something what's nice and you contract some indices, you get generalized Ricci tensor, which is tensorial, and it will be the right thing to re-express the equations of motion of the supergravity. This is just the NS sector, but the fermionic sector could be repackaged in a nice way too. If I take all my forms, I construct the curvatures out of them and wedge it with this exponential of 2 form B, the one from NS sector. I'll call this capital F. And then, so as I said before, the even forms are for 2A theory and odd forms are for 2B theory. I can rewrite my my equations of motion concisely as this. So this is the NS sector with the source of RR forms. By this bracket, I mean the Mukai pairing I described before. So you know, I constructed this guy. This is some form. I reinterpreted it back to the spinors, and I construct this guy and take a Mukai pairing, and I construct this equation. It would be my equation of motion for NS sector with F as sources. RR sources, and the one for RR sector is super simple. It's just the derivative of this F is 0. So this is really like an exterior derivative of F is 0 on this capital F. So that's a nice way to repackage your equations of motion. You can go extra mile and do the same stuff for fermionic. This is just the bosonic content of supergravity, and you can do fermionic content and look at the supersymmetric transformations, how you can repackage stuff in ODD. But this is enough for now. So yeah, so this, yeah, any question at this point, maybe before I move further?
Yeah, can I ask about the Einstein equation that you had there? RAB. So it looks like RAB should be symmetric in the indices, right? But gamma should be anti-symmetric. Am I missing something?
Why is that? Oh, but I think no. Why is that? Is that Fritzo, do you know if you're there?
Maybe it's the two form. Maybe it's
like sorry, now I lost the screen. Sorry.
Maybe it's a two form valued.
Yeah, this is definitely anti-symmetric.
Sorry, what's the question?
I'm not. Yeah, Linus asked about this object is symmetric in A and B, right? The generalized Ricci.
Wait, I don't think so. I mean, if you have a torsion, then it's not skew-symmetric. Then it's not symmetric, right?
Yeah, but this seems like the source would be just for anti-symmetric part of Ricci, right?
Let's see.
Which is rather strange.
Yeah, I don't know. Sorry. Yeah, I don't really remember.
Could it be that it's not the Ricci tensor at all, and it's just the contraction of two indices in the Riemann tensor?
I mean, it is the generalized Ricci. It's not the normal Ricci.
Right.
But it's still weird.
But I guess you still have 1 up and 3 down.
I think there's a way to define the generalized Ricci tensor so that it's anti-symmetric instead of.
Okay.
symmetric like we're used to. I think
see.
maybe that's the solution.
Oh, no, maybe. I'm sorry. I think it's because this guy, right? These are spinor indices. So it would normally have like a doubled space-time indices, and you probably do this, right? So it's really antisymmetric in these spinor guys, but this is what that is, right? These wouldn't be the same indices you would normally get when you define it through this construction. Yeah, sorry, that's that, right?
But gamma with symmetric indices is just one. I mean the symmetric mu nu. They're all products of gammas are all antisymmetric in mu nu.
Sorry, I just found that the way we are doing this is that this A and B, they kind of like B is kind of a dotted index. So one of them is from so you decompose your space into two parts, the generalized space into two eigenspaces of the generalized metric, and then one index is from one guy and the other one is from the other one.
I see.
Yeah, that makes more sense.
Okay. Sorry about that. Okay. So there's a yeah, maybe yeah. Is there anything else? Clearly I didn't do a good job, but maybe something else I would know how to answer. If not, then I'll move forward. And there's a way to generalize even further. So you can generalize geometry and construct this exceptional generalized geometry. And as you know, the supergravity has this extension in one dimension higher, and that's M theory. And M theory. What's nice about this is that it merges. And then price you pay for this is that you have. Yes?
Ondra, could you repeat? We haven't. We have lost you for like 10 or 15 seconds.
Oh really? Where did I stop?
You talked about duality and then you disappeared.
So in M theory, you do this uplift of supergravity of 2A actually, and there's a nice way to repackage and merge the NS and R sector into one thing, and really the objects will just hide in this metric and this tree form. And the price you pay for that is that the underlying group, the structure group of your manifold is now this ED group, the exceptional group, and ODD sits inside. So if you remember from your Lie algebra classes, what's the Dinkin diagram of ED? It's almost like ODD, but with extra prolongated lag on one of the spinor ends. So you see that ODD really sits inside. If I chop off this guy, and it produces this ED group. So these are quite complicated objects, ED groups, but you can see that if you go, actually, if you're chopping off things from this side, you're going to lower dimensions, and you can see that when you chop off enough dots, you start getting some low-dimensional coincidences in Lie groups. So if you don't like ED groups, you can, for instance, chop it off here, and what do you get out of it is this, which is spin 5, right? So spin 5,5. So we would identify that with E5. And if you go one further, it's even simpler. You see that I can just string this guy up, and I can reinterpret this as a SO5. So many examples in this exceptional field theory are studied for these low dimensional situations where the ED is not that horrible, and it's actually some of those groups we're familiar with. What's not great about ED is that it doesn't have quadratic invariance, so there's not really nice generalized metric, but that's fine. I mean, we can work with field binds, not field binds, and study the frames on this manifold. It's anyway better description even when there's generalized metric. And so yeah, as I said, it nicely unifies this. This was the R sector, and NS sector was sort of generalized metric on this guy. So now we'll be just put in one exceptional tangent bundle, and that thing varies in dimensions. It starts nicely. Well, nicely. It's this object where you have two forms. Vectors and 2 forms and 5 forms, and there could be higher things when you go to lower dimensional ED groups. Higher dimensional ED groups. So there could be more unruly objects. It's not this nice generic Dm plus D star M. And the ED group acts in some interesting way on this exceptional tangent space. So you can another nice way to see that this is consistent with the previous generalized geometry considerations is that if you restrict this exceptional tangent space on a manifold which is globally of kind MD cross S1, you can do the dimensional reduction of these guys and use some dualities, and you will see that it will actually split to the generalized tangent space and the S plus, because you get to a supergravity. Okay, yeah, right. So now I'm almost at the end. I wanted to advertise some work we did with Friedrich, who's sitting here, and 2 other people, Mark Buckton and Dan Waldron. And yeah, but before I maybe get to this, because that's just some application of the previous stuff, and maybe I'll ask Friedrich to join the discussion. I can maybe give you an example of, well, maybe I'll do it later because there's not really that much time. But maybe are there any questions to this, because this is really the end of the general discussion.
Yeah, I wanted to ask, so towards the end, when you were talking about this exceptional theory, and you had some examples of the groups and how the generalized space looked, and you always had this tangent space that it was always there, and then you add some forms. So is the structure of the underlying current algebroid always there, and you just sort of pick out the special?
Sorry, can you repeat that?
Well, yeah. So you would have the structure of the current algebroid always present here, right? Because you can always project to this tangent space. So that's like what is the, let's say, connecting thing to the previous example with when we had just.
Oh yeah. So here in this. So in this exceptional generalized geometry, you also, yeah, I didn't get to that, but you can do the similar things. You can define Dorfman kind of derivative. You can define current bracket, and things work out very similar to the previous situation. So yeah, it's just maybe more complicated, mostly because it's this ED group in the background, and also for other reasons. But yeah, you can define that differential structure there, and also, yeah, as I said before, this T star M, it generates the gauge transformations. Here will be the D you'll be taking d of this guy and d of this guy, so you'll have some shifts in with 3 forms and 6 forms. So it'll be again some natural gauge transformations of your M theory. So yeah, it's really very much similar, except when you go to higher dimensions and things get more complicated. These extra objects are no longer just higher forms. It's something more complicated and harder to work with. And ED groups are just terrible.
Yeah. Okay. Thank
Yeah.
you. Thank you.
So I guess if basically with Friedrich and other people who are not here, we're studying we're sort of trying to put this generalized geometry and exceptional generalized geometry on an equal footing and define this object called algebroid, which is exceptional G-algebroid. It's just something what nicely geometrically encompasses the definition of a yeah, I'm sorry. Sorry, I got a little lost. So we're sort of defining some encompassing language for generalized geometry and exceptional generalized geometry, and we define this object called G-algebroid, which is really based on pronouncing that structure group in the background ED or ODD, and then appropriate tangent space, exceptional tangent space or generalized tangent space. So this would be either TM and T star M, or the stuff from M theory you've seen, and then we're applying our formalism to sort of partially answering what are the sort of so-called generalized parallelizable spaces. These are important in compactifications of M theory. So in M theory, I mean, you can compactify on tori, but if you want to know more general spaces you can compactify on, it turns out that nice class of examples, if not all of them, are these so-called generalized parallelizable spaces. Those are spaces which are not parallelizable in the usual sense, meaning that they don't have this globally defined non-vanishing frame. But if you look at their exceptional or generalized tangent space, they do admit globally defined non-vanishing frame in this generalized tangent space or exceptional tangent space. So these are generalized parallelizable spaces, and we study these guys, trying to give non-trivial examples of those. There's some caveats we're trying to fill, and that's that many things are well behaved and nice for E6 and lower theories, but going to E7 and higher, things get complicated, and we're looking into that in probably the future work, and there's also a nicer conceptual description of stuff which fits in the framework of graded geometry. It's bounded with so-called Leibniz algebroids, so they will be also discussed later on. And nice thing about this framework is, for instance, that you see sort of on the nose that U-duality is compatible with the M-theoretic equations of motion. So what's sort of not very apparent in the usual language, it's kind of you don't really have to go extra mile to check U-duality compatibility. And I guess that's that's pretty much it. There's some applications we use this generalized parallelizability to construct an example of spherical T-duality, which has been discussed in literature, but hasn't been really filled in details. It's been only considered in its topological aspects, but we have like a nice geometric model for it, and also have some. I guess this is all I wanted to say. Hopefully, it wasn't too hectic, and yeah, I'll be happy for any questions. Oh, now I lost the sharing, I guess. But I don't need to share for this moment.
So can I ask about this spherical T-duality? So is this the same as what Matai and people have been doing, the topological story? Or...
Yes. But I don't like to. I don't want to call it T-duality. That's why I agree, because it's not really T-duality. It more like fits into the framework of M theory, and we because there's some. It's really M theoretic duality. It's just that that underlying Leibniz algebra we have for it is built on a group SU2 cross SU2, and they call it spherical T-duality because it's modeled on some spherical vibration over manifold, right?
Yeah.
But those forms in the story, they are really the M theoretic ones. So it's more of a spherical U-duality.
So yeah, I remember looking at this at some point, concluding that exactly as you say, that T-duality is not a T-duality. It doesn't generate solutions to the beta function equations or anything like that. But is there some can you say more about exactly where it fits? You say it has some M theoretical interpretation. Can one say more about
it? Right. So okay, yeah, let me share.
I mean, my question is, simply put, the question is it relevant for string theory or not?
So you have these. Okay, let me start a new page. So okay. So as I said before, so really what we found is like a suitable generalized parallelizable space for as a blueprint for the spherical T-duality, and it's built upon having this SU2 SU2. So this is three-dimensional and three-dimensional. So you have dimension 6, and you can see that if you construct so its tension space is six-dimensional, and if you actually see it as if you factor out one of these SU2s, you have a generalized tension space over it. So if this is IM, you'll have TM plus wedge to TM, and this is acted upon by E3, by this guy. So that's the SL2 and SL3. So it's really a particular duality in this E3 geometry built upon this space SU2 cross SU2 when you pull this back over a manifold, and this is your S3, right? So you can pull it over a manifold. You can create this spherical vibration over some generic manifold, and you can, by different pullbacks, you realize different U-duality frames in this E3 geometry.
Right. Okay. So the statement is it's not T duality, it's U duality.
Yes, yes. In E3, yeah, in E3 compactification of M theory.
Yeah. Okay.
Yeah, I guess for them, I don't know. I guess they didn't really see it in M theory. They just saw a natural generalization of not fibering your space with S1s, but with S3 straight, and just worked out what's the associated topological T duality there. But it really fits in the framework of M theory.
Yeah. Okay, thanks.
Any other questions for Ondra or comments?
Maybe a comment. So this is all at all this exceptional and generalized stories at the supergravity level, right? But we know that in string theory we have also high derivative corrections, right? There are alpha prime corrections and G string corrections. Now the fact that there doesn't seem to exist a Riemann tensor here suggests that it's going to be difficult to incorporate those corrections in this framework. Agree?
I guess, yeah. I mean, I think you can define in a similar sense, and now I'm not really sure. Maybe if Rizzo is still there, he can join discussion. But I think you can still define some kind of Ricci, right? When you restrict yourself on section constraint in a similar way, like you still have a connection as you have in generalized geometry, and you construct this commutator of connection minus the d of the appropriate current bracket in the exceptional geometry, and you get something what's not tensorial, but you can restrict yourself to isotropic subspace, and you still have a well-defined section of some curvature. I don't know if that's something you have in mind, but
I'm happy with that you can define a Ricci tensor, but you can't really define a Riemann tensor. And what you need to higher derivative invariance is actually the Riemann tensor.
Right. Yeah, that's true. Okay. Yeah, I don't know.
That it's not possible, but it suggests that it might be at least difficult.
Maybe really. So this is also just exceptional generalized geometry. Maybe you really have to go to full-fledged exceptional field theory to be able to, right? Because this is really just an analog of generalized geometry where you solve for section constraint and you're ordered physical space, and just the remnant of that doubled or exceptional space is just that physical part under the anchor map, and the exceptional tangent bundle above it. But maybe if you generalize further and go into exceptional field theory, you can define objects like.
But I don't think that overcomes the problem that you don't have a Riemann tensor.
Okay. Yeah, I don't know. I haven't thought about that. Is there any? Do you see anything anywhere, or like in the literature where people would be considering like natural generalization of Riemann curvature, or?
So what is your question?
No, whether I don't know. I have no answer for your comment, or nothing to add. But if you know about people considering this problem, or it's been just not answered at all.
I think you can more or less prove in the generalized ODD case. I think you can basically prove that there doesn't exist an unambiguous Riemann tensor. Some work by Holm and Spivak, I think.
Okay.
Any other questions or comment?
Yeah, I wanted to comment that maybe it's still feasible that maybe one cannot construct the Riemann tensor, but maybe these higher corrections in the beta functions, that they might be still doable. I don't know if that makes sense.
It's possible. It's just a hint that it might be difficult.
Right.
If you had a Riemann tensor, then you would have somewhere to start.
I see. Yeah.
And you need the full Riemann tensor when you're constructing the higher alpha prime corrections. You can just go with the Ricci or.
Yeah, for some correction. For example, the first correction for the type 2 string is Riemann to the 4th. Plus some other garbage, but the Riemann to the 4th is really.
I see.
Okay.
Okay, so if there are no more questions, I think I want to thank to Ondra for a very nice talk, and we will see each other next year, I think. So bye.
Thanks.
Bye. Bye.
Bye.